when one of the principal stress okay, is equal to 0 and the other can either be positive or negative. Okay, so I'm going to sketch this out. What do I mean by that? So if we have Mohr circle, now all these I'd like to remind you, all these are in terms of 3D Mohr circle. Okay, I'd like to remind you, all these are in terms of 3D Mohr circle. Right. So this is normal stress. This is shearing stress. Element rotate clockwise, anti-clockwise. So it's when one of the stress value, okay, is positive and the other one is equal to 0. So this is 1 or 2. Okay. So this is your stress A. And this is your stress B. So as I said earlier, is based on a 3D Mohr circle. So this is the biggest circle you can get. Okay, so maybe you have 2 more circles doing this. Okay, you got 1 circle down here. And then you have the other circle down here. Okay. Right. So stress A is your minimum stress, which is equal to 0. Stress B is your maximum stress, and the other 2 planes, okay, the circle are within the bigger circle. Okay, so you have to check whether is it the smaller circle or the bigger circle that you have. And then the other condition, right, is where you have a minimum stress which is not equal to 0, but your maximum stress is equal to 0. So you have another condition. So again, the normal stress and then you have your shearing stress. Okay, then this is where your stress A and stress B are. Okay, so over here, this is your stress A, and over here, this is your stress B. Okay, and then you have the other 2 circles. Over here. And another one. So the main point is this, okay? Make sure that the circle you analyze or the element you analyze, that plane generate the circle with the biggest diameter. Okay. Then you can apply when this is the condition, then you can apply Like for the left hand side, you can calculate that tau max is equal to stress B divided by 2, right? And this is equal to your absolute value stress max divided by 2. Okay. Whereas on the other side, you will have your tau max will be equal to stress A divided by 2, right? So this is equal to your absolute value of stress mean divided by 2. Okay. So again, this is only true, right? If the biggest diameter circle, one is at 0, and the other one is either positive or negative. If it's not in this condition, then we have to have another criteria. Okay, sorry, another form of the expression of Tresca, okay, and which is equal to tau max is equal to half, right, absolute value of stress max minus by stress mean. Okay, so this is equation number 3. So in equation number 3, as you can see, right? So equation number 3 is valid when the principal stress are not equal to 0. Okay, so I have an example where we have so you have your normal stress, and then you have your shearing stress. Okay, and then this is the diameter of your circle, the biggest circle. Okay, so this is your stress A, and then this is your stress B. And again, the other two planes, right? The circle are within, all right? So this is one with a circle. And then we have another one. So for this case, right, we know that tau max is equal to half stress A minus stress B. So this is also equal to half, right? Or I'll put here stress B minus stress A. And this is in fact equal to maximum minus stress minimum. Okay, and therefore stress max or shearing stress max is equal to half absolute value stress max minus bar stress mean. Okay. Right. So these are the criteria for Tresca. So I'll show you a few example of how it really works with Mohr circle. So let's look at a short example. Okay, example number 1. So we were given that the material property right stress yield is equal to 100 megapascal. Okay. So based on Tresca criteria, and this is important, which I did not mention earlier. So based on Tresca criteria, right, it is assumed that the stress yield in tensile is equal to stress yield in compression. This is the criteria that he makes, okay? Or condition, not criteria. It's a condition. So what it means based on Tresca criteria, stress yield in tensile is equal to stress yield in compression. Okay. So from here, we know that our tau max, so this is our material property, right? So this is equal to stress yield divided by 2, so it's 100 times 10 to the power 6 divided by 2. So this is equal to 50 times 10 to the power 6 Pascal. Okay. So now, if we have an element now, right? So this is our X and Y, and we also have a Z. Okay. So from here, we draw a element. This element is not very good. I'll tell you why later on, because you don't know which one is in plane or which one is out plane. Now this is better. So we know that this is equal to 150 megapascal. And we know that this is equal to 25 megapascal. And the stress Z is equal to what? 0. Okay. So when you draw this out, right? Right. So I will call this 50, 100. Okay, so that is equal to 200. And our shear stress, this is 50